Welcome to this explainer. We're diving straight into the invisible forces of thermodynamics that run, well, pretty much everything around us. From that pot of water boiling on your stove to the massive industrial power grids keeping our cities alive, we are talking about the absolute fundamentals of heat.
We're going to break this all down logically today, looking at the two types of heat, the physics behind phase changes, the thermal energy math, high-efficiency storage, and we'll wrap up with HVAC and industrial power.
Section 1. Two types of heat. Let's start with a scenario we've all seen. You've got a pot of water on a hot stove. It gets hotter and hotter until it hits exactly 212 degrees Fahrenheit. But then it just stops. The temperature absolutely refuses to budge, even though the burner is still on full blast. So where on earth is all that energy actually going?
Right, so this perfectly highlights the hard boundary between the two forms of heat. First up, sensible heat. This is exactly what it sounds like. The heat you can physically sense and measure with a thermometer. It changes the temperature, but the physical state of the substance stays exactly the same. But then you've got latent heat. This is the energy that actually changes the state of a system, like turning liquid water into steam. But crucially, it keeps the temperature completely flat. You know, the history behind the name is actually pretty fascinating. Latent comes from the Latin word latens, which literally means lying hidden. A Scottish chemist named Joseph Black came up with this around 1762. And get this, he was actually commissioned by Scotch whiskey producers. They were trying to optimize their fuel and cooling water for distilling. Black figured out that melting ice absorbed massive amounts of heat without its temperature changing one bit. The energy wasn't showing up on a thermometer at all. It was literally hidden inside the substance. A real game changer.
Moving on to Section 2, the physics of phase change. To really grasp where this hidden energy is hiding out, we need to zoom way in and look at the microphysics of these molecules.
Down at the atomic level, sensible heat basically acts like a massive cup of coffee for atoms and molecules. It makes them move faster, increasing their translational, rotational, and vibrational motion. They just jiggle a lot more, and we measure that extra jiggling as a higher temperature. Latent heat is a whole different beast. It is the specific energy needed to literally break or overcome those stubborn intermolecular bonds holding a liquid or solid together. So instead of making things vibrate faster, every ounce of that energy is consumed by the physical act of ripping the molecules apart to force a phase change. This dynamic is absolutely crucial. When you have a phase change like melting or boiling, that process is endothermic, meaning it actively absorbs and increases latent energy to break those bonds. On the flip side, freezing and condensation are exothermic. So when a gas collapses back into a liquid or a liquid into a solid, it suddenly releases all of that hidden latent energy straight back into the environment. Section 3, calculating thermal energy. Now that we've got the underlying physics nailed down, let's take a look at the mathematical language engineers actually use to calculate these energy needs. Here is how the math shakes out. For sensible heat, the formula is QS equals mass times specific heat times delta T. That delta T is just the temperature differential. So sensible heat is entirely dependent on how much the temperature actually changes. But check out the latent heat formula. QL equals mass times HL, which is the specific latent heat content. Notice what's missing? Yeah, there's no delta T at all. Calculating latent heat totally ignores temperature because, well, during a phase change, the temperature doesn't change. You just multiply the mass by its known latent heat capacity. Simple as that.
So why do we even need both? Well, we can't forget the first law of thermodynamics. Energy cannot be created or destroyed. Any system has to maintain a flawless energy balance between the heat in and the heat out. Engineers absolutely have to calculate the total heat, which is the sensible plus the latent heat, to design systems that keep that energy equation perfectly balanced.
Section 4. High-efficiency energy storage. Getting this math right unlocks something amazing, the ability to engineer incredibly efficient industrial setups, specifically using phase-change materials or PCMs. The massive takeaway here is the sheer density advantage. Because phase changes happen at a constant temperature without huge thermal swings, latent heat storage using phase change materials can hit storage densities 5 to 10 times higher than your standard sensible heat storage. Just think about that for a second. If you're storing solar energy, instead of just heating up a giant bulky tank of water, you use a phase change material that melts and absorbs mountains of hidden energy.
Then at night, it cools, solidifies, and releases all that power back. And it does the whole shebang, taking up a fraction of the physical space. This mind-blowing energy density actually brings up a huge industrial question. Why is steam considered vastly superior and honestly way more hazardous than boiling water? I mean, they are both sitting at 212 degrees Fahrenheit, right?
The secret is the enthalpy of condensation. Steam is not just hot water. It is a massive floating bank of hidden latent energy. When steam hits a surface and condenses back down into a liquid, it violently dumps all of that absorbed, hidden latent energy directly onto that surface as sensible heat. That is what gives you continuous heating at a constant temperature. It's exactly why steam is the ultimate heavy industry heating medium, but also why a steam burn is so uniquely devastating compared to a hot water burn. You are literally getting blasted with hidden energy.
Section 5, HVAC and industrial power. Let's scale things back from heavy manufacturing to your own living room and see how these exact principles rule your personal comfort.
At its core, a basic refrigeration cycle is just a heat mover. It absorbs heat in the evaporator inside your house, which forces the liquid refrigerant to boil into a vapor, and then it rejects that heat outside of the condenser, forcing the vapor back into a liquid state. It is constantly balancing the tons of refrigeration, or TRs, entering and leaving. That perfect energy balance scale we talked about earlier, it is happening right now, just outside your window.
But here's the catch for true human comfort. An HVAC system actually has two totally distinct jobs. First, it has to handle the sensible load. That's physically lowering the temperature of the air in the room. But equally critical is the latent load. The system has to dehumidify the space by forcing a phase change, making the invisible water vapor in your air condense into liquid on the cooling coils. If your AC only cooled the air but ignored the humidity, you'd basically be sitting in a cold swamp. No thanks. That is exactly why modern fan coils are designed with both sensible and latent cooling capabilities.
So we've seen how these invisible thermodynamic forces dictate our physical world. But as we look ahead to transitioning away from fossil fuels and dealing with the intermittent nature of wind and solar, it leaves us with a huge question. How will our mastery of phase change materials and latent heat storage reshape the efficiency of a fully renewable global energy grid? Could the ultimate key to our energy future literally be hiding in the physics of a phase change? Definitely something to think about. Thanks for tuning into this explainer, and we'll see you next time.